This lecture, we're going to start talking about the postulates of quantum mechanics. Postulates. What's a postulate? Assumption. Okay, so the basic ideas. So a postulate is something that you cannot prove. Okay, that's the most basic of all the assumptions. So if you can't prove it anymore, you just assume it's true. And for as long as you don't encounter any contradictions, you accept it. Okay, so what are the postulates of quantum mechanics? There's several. The very first postulate, postulate number one, says that for any system, okay, there is a function which we represent by the Greek letter psi. So that's the Greek letter psi, which describes the state of the system. All accessible information about the system can be obtained from psi. So anything you want to know about the system, if it's available, you can find it in psi. Okay, so in other words, if you know someone who's a know-it-all and you want to give him a nice gift, give him a shirt that has psi printed on the shirt. Okay, so psi gives you all accessible information about a system. So psi is called the state function or the state wave function, or just we simply say the wave function. So it depends on Q and T. What's Q and T? Q here represents the coordinates of each and every particle in the system, and T would be the time. Okay, so psi, then you can imagine psi for something like a sample, a macroscopic sample of matter is going to be a huge function. It's a function of the coordinate of each and every electron and nucleus in your particle and time. Okay, so for our purposes, we're going to treat the nucleus of an atom as just one particle. Okay, so we're going to take all the neutrons and the protons all together as just one particle. So the nucleus of an atom will be taken, we're just going to deal with it as just one particle. Then each electron is treated also as one particle. Okay, so upon how many coordinates does the state function for a helium atom depend? 1, 2, 3, 4, or 5. Helium atom has a nucleus, right, of 2 protons plus neutrons, right? Which can vary depending on what isotope you're dealing with, right? And so that's counted as one particle. How many electrons does our helium atom have? 2 electrons. So how many particles do we have? 3 particles. So that's the nucleus plus 2 electrons. Okay, so it will depend on 3 sets of coordinates. Consider a one-particle system. Let's say you're just dealing with a system of just one particle, and that particle happens to just be constrained to move in one dimension, just along the x-axis. How many variables, upon how many variables would our state function depend on? What would you need to locate the particle? Just one number, right? Because it's just confined to the x-axis. So psi will just be a function of x and time. So how many variables then? 2 variables. Consider 2 particles constrained to move in a plane, the xy plane. So no 3-dimensional movement, just on a plane, flat surface. How many variables does the state function depend on? So let's call those 2 particles particle 1 and particle number 2. So how would you locate particle 1? You're going to need 2 variables, right? So you need x1 and y1. And to locate particle 2, you're going to need x2 and y2. And then time. So it depends on how many variables? 5. All right. Now, the Born postulate, this is one of the postulates, but we're not going to give it a number because we're going to see later that this is going to be a corollary to another postulate that we're going to make. But for now, this is a postulate that we're going to introduce this because this is traditionally how this psi is interpreted. Okay, so psi itself has no meaning, no physical meaning, okay? And the reason for that is psi itself can be the value of psi can be a complex number. If the value of something can be a complex number, then it has no physical significance. It cannot have a physical meaning because everything in our physical world is associated with a real number. Okay? So psi itself has no physical meaning. So if you want something out of psi that has a physical meaning, you extract a real number from psi. So one way you can extract a real number from psi is to take its the square of its absolute value. Okay, so multiply psi by its complex conjugate. Psi star is a complex conjugate multiplied by psi. That gives you the absolute value of psi squared. That is called a probability density function. What does probability density function mean? Let's illustrate that with, let's say you have a particle that's constrained to just move in one dimension. Okay, so here you have a one particle, one dimensional system. So psi is just a function of x and time, right? So if we were going to take the square of psi, so if you take the square of this, that means whatever it is, it can be complex or real, takes its complex conjugate, multiplied by the function itself, you get psi squared, right? Integral of psi squared dx, okay? If you integrate psi squared dx from x1 to x2, that is going to be interpreted as the probability of finding the particle between x1 and x2. Okay? So, in other words, psi squared dx, okay, is the probability of finding it between x and x plus dx. The value of psi squared at x, multiply that by an infinitesimal amount dx, okay, that is the probability of finding it between x and x plus dx. So, since psi squared dx is the probability of finding it between x plus dx, what is the unit for psi squared? What's the unit for probability? A probability is just a unitless number between 0 and 1, right? So what's the unit for x? A unit of length. So something like meter would be an SI unit. So what would be the unit for psi squared? Per meter. So in other words, when you say probability density, what we mean is probability per unit length. You have to integrate it over a finite length to get the actual probability. Or you multiply it by an infinitesimal distance to get the probability within that infinitesimal distance. Okay? So psi squared is called a probability density function. What if we were doing 3 dimensions? Three dimensions, psi is a function of x, y, z, t, right? So your psi squared, then, you'll have to integrate it, okay, with respect to x, y, and z. Integrate it over an infinitesimally small volume with length, width, and height of dx, dy, and dz. So this is dv. Okay, so this thing right here is a volume unit. This is in SI, this would be in meters, this would be in meters, this would be in meters. So what would be the unit for psi squared if it is if it's a 3-dimensional function? Per cubic meter. Anything per cubic meter, anything per unit volume, okay, per unit length, per unit area, that's called a density function. So mass per unit volume is what? Your first encounter with the word density, right? Density of an object is mass divided by volume. Mass per unit volume is the mass density. So the complete phrase for that is actually mass density.
I didn't get what you erased. It would be integrated from what to, I think you had x squared on the top.
For which one? The very first one?
For the integral, you had it integrated from, I didn't get what you had on the bottom.
before this one?
Yeah.
For the one-dimensional system?
Yeah.
Oh, if you have a one-dimensional function, sine squared dx, if you integrate it from, let's say, from x1 to x2,
Okay.
so from x1 to x2, within that interval, then the value of that integral, that's a definite integral, right? So that's just going to come out to be a number.
Oh, I didn't know you just used a basic example like that. I thought you put something in particular.
No, that's just a generic, x1 and x2 would just be a generic pair of locations. So this is going to be the integral of sine squared dx from x1 to x2 would be the probability of finding it between x1 and x2. Okay? So, now, let's talk about well-behaved functions, because psi must be what we would call a well-behaved function. And so, psi must be a normalized, well-behaved function. Okay? And why do we want it to be well-behaved, and what do we mean by well-behaved? Okay. We want it to be a normalized, well-behaved function because, remember, our interpretation is integral of psi star psi over all possible locations must be equal to 1. So when you see this symbol right here, integration, and your integration variable is tau, that simply means integrate over all possible locations. Okay? So the integral of psi star psi over all possible locations must be equal to 1 because that's our interpretation of psi squared. Integral of psi squared over all possible locations must be equal to 1 because it's psi squared is a probability density function. So a well-behaved function is one that is single valued. What do we mean by single valued? For any given location, psi squared can only have one possible value. Why is that? Well, because we have to interpret it as probability density, it must be unique. It has to have a unique value at a given location. What if I were to plot psi versus, let's say, x, and my psi looks like this? Well, at this location, I got 2 possible values of psi. Which one do you pick? So that's not acceptable. So that's a function that is not single valued. For a given x here, it has 2 possible values. Over here, it has 1, 2, 3 possible values. So it has to be single valued for it to be acceptable. Okay? Whatever psi is, it has to be single valued. It must have a continuous first derivative with respect to the coordinates. Okay? And the reason you want its first derivative to be continuous is so that the second derivative exists. Okay, if the first derivative is continuous, then you can take the second derivative of the function. Why do we want that? Because we are going to postulate, in another postulate, we're going to say that the way we solve for psi is to solve what's called the Schrodinger equation, which is a second order differential equation. Okay? So we must be able to take the second derivative of psi. Okay? And that's just a postulate, because we're postulating that how we solve for psi is to solve what's called a second order differential equation, and that requires us to take the second derivative of psi. So we want the second derivative to exist. All right. Now, finally, a well-behaved function is one that is normalizable, or what we would call quadratically integrable. Okay? What that means is, if you were to integrate, okay, the function over all possible space, then it should come up to a finite value. So it cannot approach infinity. Your psi cannot go to infinity. Its value cannot blow up, okay, in regions where your system can exist. Okay, you cannot have an infinite probability of finding it at a particular location if it goes to infinity. Okay, so an exception will be an unbound system where your psi can be. We'll talk about that some other time. Okay, where your psi can be is not bound, so there's no restriction on where you can locate your particle. In which case, it doesn't have to be normalizable or quadratically integrable, but it still cannot go to infinity. It can oscillate okay, as you go to infinity, positive or negative infinity, but it cannot go to infinity itself, the function. So that's normalizable and quadratically integrable. By the way, this condition right here, okay, that this value is equal to 1 is called the normalization condition. Okay, so we say that the square of psi, if you integrate over all space, must be equal to 1 if we insist that that is a probability density function. So that's what we mean by quadratically integrable. Quadratic means what? Second power, right? So if you square it and then you integrate it, you should get a finite value for the function to be called well-behaved. For psi itself, okay, psi must, that integral must be equal to 1. Then you say the function is normalized. Okay, so let's talk about normalizable functions then. A function f is said to be normalizable or quadratically integrable if the integral here, that I've written here, integral of f star f d tau is a finite number. Okay, what did we say d tau meant? Integration over d tau simply means integration over all possible locations. So if your particle can only be in one dimension, it can be from x equals negative infinity to positive infinity. But if you're going to confine your particle to, let's say, negative 1 to positive 1, then the integral over d tau would be from negative 1 to positive 1. Okay? So integrating over d tau means over all possible space where the function is applicable. So it could be, for example, from negative infinity to infinity. Now, to normalize your function, okay, you simply multiply it by a constant n so that the integral here is equal to 1. So if this is equal to some finite number, then we say f is normalizable. If this happens to be equal to 1, then we say f is normalized. Okay, so let me repeat that. If integral of f star f d tau is equal to a finite number, what do you call f? F is normalizable or quadratically integrable. If that finite number happens to be 1, integral of f star f d tau is 1, then we say f is, not only is it normalizable, it is already normalized. So we say f is normalized. Okay? So, let's look at this example. Suppose this integral is equal to 5. Okay, what do you call f? Is it normalized? No. Is it normalizable? Yes. So, how do we normalize function f? Well, let's define g to be some constant times f. Okay? So, what would be the integral? We're going to look for n so that integral of g star g d tau is equal to 1. Okay? So, how are we going to do that? We're just going to substitute nf for g. So that's your g, right? That's nf star times nf, that's your g, d tau must be equal to 1. How do I solve for n? What is nf star? Well, how do you take complex conjugate? Every time you see an I, replace by negative I. And if you just have a variable representing your number, you don't know if it's complex or real. N can be complex or real. F can be complex or real. So you just star it. Right? So this is going to be N star, F star, and F d tau is equal to 1. And I can factor out a constant for my integral, right? So that comes out n star n integral of f star f d tau is equal to 1. What's the integral of f star f d tau? Let's solve for n star n, which is equal to 1 over the integral of f star f d tau. Right? So what is our f star f beta? And what is this, by the way? This is just absolute value of n, right? Squared. It's 1 over 5. So what is absolute value of n? 1 over square root of 5. So f is not normalized, okay? But it is normalizable. And how do you normalize f? You multiply it by 1 over square root of 5. So we say g, which is 1 over square root of 5 times f, is a normalized function. Okay? Now, what about 1 over, negative 1 over square root of 5 times 10? Okay. What if, just one more. What if we have g equals negative 1 over square root of 5 times f? Is that also a normalized function? Yes. Because all we want is for the n, absolute value of n, to be 1 over square root of 5. Right? So we're going to continue this next time.